Hello and welcome. Today we're going to be talking about Warhammer 40k dice math. This is part 2. If you haven't seen part 1, that's where we focused on single d6 probabilities. Today, however, we're going to be focusing on 2d6 probabilities as well as much larger pools of dice. Specifically, we're going to be talking about charge rolls and psychic tests. Some of it is going to be basics of charges and psychic, and some of it is going to be far more advanced, so I encourage you to listen all the way through, even if you think you truly understand charge and psychic probabilities. And honestly, if you don't find anything that you learn, then just give me a dislike, but I think you'll find something that you didn't know beforehand. So just to reiterate what we've already talked about in our first episode, dice rolls are independent of each other. If you rolled a lot of 6s once, it doesn't mean you're going to be rolling a lot of 1s later on. On a single d6, there are 6 possible outcomes, and each of those has an equal probability, so about 17% chance. And you can see on the left here, we've got a graph of what that probability looks like, and you can see it's totally flat. However, 2d6s do not have the same probability distribution as we see with a 1d6. And we can look at that by having a little chart here, where on the top we have our first dice roll going from 1 to 6. And then on the left we have our second dice roll, also of 1 to 6. And what we can do is we can go through and add everything in each column and row and fill out this entire table. And what you'll see is that we have 2 here, 3s, 4s, 5s. It increases along the diagonal. Another thing to note is that there's one value of 2, 2 ways to get 3, 3 ways to get 4, 4 ways to get 5, etc. And then going back down at 8, 9, 10, 11, 12. And we can take this and we can put this on a graph to show the probabilities of getting any specific dice roll. And here we have on the bottom essentially the number of possibilities or ways we can get a certain dice roll ranging from 2 to 12 on 2d6. One of the things you'll notice is that the average here, 7, we have about 6 chances out of the 36 possibilities to get. So the average on 2d6 is 7, pretty clear, and probably most of us know that. But sometimes people don't understand that you actually have a more than a 50% chance to get the average. So rolling a 7 or higher on 2d6 is actually a 58% chance. So when people talk about what an expected roll is on a pair of dice, or any amount of dice, it doesn't mean that you're guaranteed to get that much. The expected value on 2d6 is 7, but you still have a 42% chance of actually not getting the value you want. And we can look at what the percentage to get any certain number is by looking at the number of ways we could get that. For example, 10, there are 3 different ways to get that, and 36 possibilities, so 3 over 36 is 1/12. But we can also look at, a minimum or greater value. This is really popular in Warhammer 40k, where we need a set number or anything higher on a 2d6. So what I've done here is I've color-coded it in. So let's say a 2, 3, and a 4 is a fail. That's color-coded red. And then a 5 all the way through 12. That'll be green. That'll be considered a success. And then we can actually kind of draw this out on our 2d6 probability chart on the top right. We can get a good estimation of kind of what this looks like in our head, a little bit more easier to understand than just some number. And you can see that essentially one way we can calculate the value of succeeding is actually looking at the value of failing, because that the percentage chance of failing plus the percentage chance of succeeding is 1. So there are 6 ways, 3, 2, 1, 6 ways to fail. 6 out of 36 is a 1/6 chance, so that means there is a 5/6 chance of succeeding. And we'll use that kind of technique numerous times throughout this little PowerPoint. And then over here, we can see what the chance is to get a 9, 10, 11, or 12, 4, 3, 2, 1. That's going to be a total number of probabilities of 10 out of 36. That gives us about a 28% chance of success getting a 9 or higher on 2d6. And what we can do is we can plot these all out to get a probability of a minimum value on a 2d6. So pretty obvious, if you need at least a 2, you have a 100% chance to get it, because the lowest thing you can possibly roll is 2 1s, so you have a 100% chance of getting at least a 2. and this will decrease in a non-linear fashion all the way down to 12. It's impossible to get a 13 because there's no way to get that on a 2d6. And then what we can do is we can look at how these percentages change. So going from needing a 9 to needing a 7 takes you from about a 28% chance at 9 to a 58% chance at 7. So just by changing the value needed by 2, essentially you can look at the difference here, and out of 100 total rolls, you would get 30 more successes if you changed your needed roll from a 9 to a 7. However, if we go a little bit further down the curve, if you go from needing 12s to needing 10s, you would actually only go from a 13 to a 17% chance. In other words, about 14 more successes over the course of 100 rolls. So if you're looking to just pump out more successes overall, essentially changing the value towards the middle of your distribution, probability distribution, is going to give you the most bang for your buck. It is worth noting that going from 3% to 17% chance is about a 6 times difference, whereas 28 to 58 is about 2 times change. However, we're looking at number of successes increased over about 100 dice rolls with perfect dice, because that gives us a more concrete value in terms of how many more things we're killing or how many more successes we get. So now we're going to use this to apply to charges. So I've drawn a few characters out here. On the bottom left we have a Blood Angels Vanguard vet. War gear is pretty clear here, lightning claws and a storm shield. And then on the right we have a White Scars with the same loadout. And then on the top we've got 2 Orc Boys. I am actually not accepting any commission requests right now. I'm totally full up, but I'll let you guys know when I have more room. So the Vanguard vet, we'll say you're each 22 inches away from the orc they want to charge. They each have a 12-inch move. However, the Blood Angels get +1 to charge. That means if he moves 12, he will need a 9-inch charge, which is about a 28% chance success on 2 dice, but he can re-roll it and get a 48%. Just to remember how we calculate that, we already learned about the 28% chance. We do is we subtract that out of 100, or 1, and that gives us a 62% chance of failure. We can square that, gives us 52, and then subtract that from 1, giving us a 48% chance with a reroll. So then we can look at the White Scars. Instead of getting +1 to charge, they get a d6 advance, and they can advance and charge. So that means they have a 12-inch move, and then essentially 3d6 to make up that last 10 inches. For the White Scars, they can move 12 inches the same, however, they can advance and charge, meaning they get an extra d6 inches to their total threat range. And then with their 10-inch charge, but we'll clump all those 3d6 together for the 2d6 from charging and the single d6 from advancing, that gives them about a 65% chance of success. And then if they use 1 CP and re-rolled that, they can get about 88%. I just clumped that 3d6 in together. It's a little bit different because you have to re-roll 1 of the d6s for advancing or 2 of the d6s for charging, but it's a close enough estimation, and we'll get into the specifics later. So right off the bat, you can see that White Scars have a higher percent chance of getting a charge. One thing to note is, when you're, about to do one of these charges, you want to have an idea of what is an acceptable level of risk that you're willing to take is. For me, if I was told that you've got a 28% chance of success and a coin flip essentially if you use a CP, that is a charge that I'm likely not willing to take. However, if I had this White Scars one, 65% with a near 90% chance of success, that is something I'd be willing to take, because you don't want to put your guys up, fail a charge, and then get totally blown off the board or just countercharged by these orcs. But the White Scars have much more of an advantage than the Blood Angels than even this little graph shows. One of the biggest reasons is that the White Scars get to roll their d6 for advancing before they decide if they actually want to charge or not. So for example, let's say that White Scars player is in the movement phase, they roll their advance, and they get a 1 on their value. They would already know that their success of charging has gone down to about a 28% chance, or once again a coin flip even if they use a CP. whereas the Blood Angels player had to actually move towards the shark with the intention of already charging him, where the White Scars does not. So if you're the White Scars player and you see that this charge is a low percentage that you don't think is worth the risk, you can just move behind a ruin. So the White Scars have the advantage of knowing what some of their rolls are, that 3d6, one of those 3d6s, before they even need to make the choice of charging. So they have this information advantage over the Blood Angels who are making the same charge. But what if the White Scars gets a 6-inch move on their advance? Well, that turns their charge into a 4-inch charge, which is a 92% chance on 2 dice, or a near guarantee with a reroll. This is something that they'd be much more willing to accept, or even trying to charge something beyond the Orc Boys. Now, more realistically, Blood Angels and White Scars are going to have a chaplain nearby who can give them the +2 to charge litany. Now that's going to take, for the same example, our Blood Angels to an 8-inch charge. That only goes from a 9 to an 8 because their inherent +1 for being Blood Angels does not stack with the charge litany. However, the White Scars don't have anything that was giving them a +2 a charge before. This way they actually get the full +2 inches from the litany, whereas the Blood Angels only get half of the bonus. You can see that on the left here, the Blood Angel essentially goes up to a 42 and 64% chance of their charges. That's still a little too risky for me, whereas the White Scars here go to an 84% on their charge and a near guarantee if they're willing to take a single reroll. So not only do the White Scars get the advantage of having more information before they have to commit to the charge, they also get more benefits from charge litanies because they don't already have an inherent +2 charge bonus. And one of these White Scars, I will change this scenario to be 24 inches away. The reason why I chose 24 is the math is the same as the 22 without the litany, and it's how many inches away many deployment zones are in the Grand Tournament packet. So you can see I planned this the entire time. So on the left here of this chart, we have the advance roll that the White Scars would get, and then the value on 2d6 that the White Scars would need to complete their charge over here, and the percentage associated with that charge without a reroll and with a reroll. So you can see, depending on your tolerance of risk, in my case, if I rolled an advance roll of 1 or 2, I don't get that about 80% chance of a charge success that I'd like, so I would instead move behind a ruin or wait to another day to charge. Or I could honestly just spend another CP and reroll my advance roll. That's another big benefit that the White Scars have over the Blood Angels. Or maybe I roll a 3 and a 4, which gives me a over 80% chance of success if I'm willing to use a CP. Or if I get a 5 or a 6, it gives me a over 80% chance of success on the charge without using a CP. So I can go into a game already knowing beforehand, if I get at least a 3 value on my advance roll with my Vanguard vets, then I will charge and try to make that charge against the enemy on the other line. So these are the type of calculations you want to do before you go even get into a game. There's no reason why you should be fuddling about thinking, oh, am I, I get a 2 on my advance roll, is it worth for me going for the charge? This is the type of stuff you can do beforehand, and one of the benefits of really playing with the same army over and over again is you can kind of do all this math just once and then use that for the next couple years before you get a codex. Now we'll change this scenario a little bit, and as you can see I put even more effort into the salamander on the top right. It took me quite a few hours, so please give me a like and subscribe for the salamander. So in this scenario we're going to be looking at White Scars trying to make a 30+ inch charge away with the +2 to charge litany for the chaplain. And you can see that this is a 0% chance to succeed. The reason why that is because even if they get a D6, a 6 on their advance, that would be 18 inches with their 12-inch move. It'd still be a little bit over 12 inches away. And even though the charge is 2d6 and they get +2 to charge, which you would think is a 14-inch charge, you can only declare if you're within 12 inches. So in other words, the max threat range of the Vanguard vet for White Scars is 30 inches. So as long as your salamander Intercessor is 30.1 inches away. There is a 0% chance of success by the White Scars to charge him. But it comes with another issue. A Intercessor has a 6-inch move and a 24-inch bolt gun. So his chance of success of being able to move and shoot the White Scars Vanguard Vet, if they go first, is 0. So you're kind of at parity here where you're both staying outside of each other's threat range. And that's good if you want to eliminate all risk and you just want to stay right outside of threat range. But if you're the Salamanders player, there's some better choices I think you can make. So instead, if the Salamanders player decides to set up exactly outside of 29 inches away, in other words, moves up just about 1 inch, then their 6-inch move plus their 24-inch bolt gun will give them a 100% chance of being in range of the White Scars Vanguard Vet, because they just move and shoot, right? There's no randomness associated with that. However, the White Scars Vanguard Vet, even with the 12-inch move, 3d6 inches of advance and charge, and the plus 2 inches on their charge litany, is about a 10% chance of success. And that is 3 5s assumed for the advance and then, the charge rolls respectively, giving them about a 10% chance of success. So in other words, the Salamander's Intercessor, that general over there, decided, I'm willing to take a 10% risk of being charged by the Vanguard Vets in order to guarantee that I can shoot them. So takeaway on this one is that expert players are going to cautiously accept risk in order to gain tactical advantages. A basic level of understanding of the game is staying out of threat ranges, and that's great. But sometimes you actually want to slightly be in threat ranges in order to gain a tactical advantage for yourself that is more important than the risk that you take from your opponent. So now we'll move into the Psychic phase. Psychers cast their spells using the same 2d6 that other people use to make charges, so the percentages here will all look very similar. As we talked about before, chance to get a 2 is 100%, chance to get all the way down to a 12 is 3%. When we look at what the chance to get a Perils of the Warp, that is when you roll 2 1s or 2 6s, it's going to be 2 opportunities out of 36 total, 1 out of 18, or about 5.5%. This chart is important to look at when we're casting our spells because we should know about how likely we are to cast our psychic spells. I think too often people assume that should be guaranteed to get their psychic spells off, when in reality some of them are, in fact, not all that likely at all. Most psychic spells live between 5 and 7, and those harder to cast spells are almost a coin flip in terms of whether they're going to go off or not. Additionally, sometimes you have to make a choice. Are you going to cast a spell with a chance to get perils? Because you don't want to be taking unnecessary risk. That's another big part of Warhammer 40k is avoiding unnecessary risk. So let's say your spell allows you to fight first, but it's your turn and you don't plan on charging with a specific unit. You may decide, well, there's a very small possibility that this spell matters for me, but there is also a small possibility that just trying to cast it will hurt my Psyker and cause the Perils of the Warp. And the last thing you want to do is have your Psyker blow up in his own, deployment zone and then kill things around him. So that choice is going to be up to you to make, but you should know that it's about a 1 out of 18 chance to have a Perils of the Warp, so it will happen as you go through your games. And sometimes you actually don't want to cast spells if they're not relevant at all to the game, because it's just giving you an unnecessary risk of accidentally wounding your Psyker. The other thing that's important to know about psychic abilities is things like Smite actually have a benefit to getting higher rolls. So you don't just succeed or fail, you can actually have 3 different states, either success or failure. For example, a Smite has a warp charge value of 5. That means a 2, 3, or 4, or a 1/6 chance is a fail with no modifiers. And then a 5 through 9 gives you 6 plus 10, 16, 24 out of 36, or about a 66% chance of success, and then another 1/6 chance of getting a super smite. And this is really key about smites, is that essentially modifiers are going to increase the chance of your success, as well as increasing the chance of super smite, which can roughly double the amount of damage a smite does. So now we'll look into how the 2d6 and modifiers math affect this. So if I am casting with someone like Magnus, who has a +2, you can see that my chance to fail goes all the way down to a 1 out of 36% chance. And then all my successes in yellow, and then my super smites in green. So you can see that the modifiers to psychic rolls increases the chance that you have to not only succeed, but also to get a super smite. And we can look at this at a chart. We can have a regular psyker here. And what I've done is I've put all the percentages chance they have to do to either fail, cast, or get a super smite. And then what we can do is we can multiply that percentage by the expected damage. So obviously a fail is going to be 0 damage, a D3 is going to be 2 damage on average, and a D6 is going to be 3.5. So we've got that regular psyker. Every time they cast smite, it's going to do about 1.9 mortal wounds on average. A +1 psyker dealing about 2.3, a +2 psyker doing 2.6, and then finally a +2 psyker who has mega smite. Think of someone like Magnus the Red, whose super smite does 2d6 damage and regular smite does d6 damage. You can see that the value of their smite is actually nearly 5 points of damage, almost double the next closest psyker. So this is really important to know when you have two psykers with different values who can cast similar spells. So let's say, for example, you have two psykers who can cast similar spells. Let's say you want to cast a buff spell on one of your units, as well as casting smite with your other sorcerer. You will do more damage if you use your +2 psyker to cast smite, because it gets more benefit from higher rolls than a regular psyker who will do less damage on average with their smites. Now what you're doing is you're trading that for a slightly reduced success in your buff spell, so you have to make that choice, but knowing that the value of a smite cast on a more skilled sorcerer or one with mega smite will do drastically more damage than one without it. Now we talked a little bit about dice before, but I just wanted to show this one so we can start talking a little bit more about variance. So on the left here we have that D6 probability chart that we saw before. On the top right we have 2d6, the probability, and then 3d6 on the bottom right here as well. And you'll start to notice a few different things and kind of different shapes taking place as you add more dice. So one of the things we can look at is what is the chance to get an extreme roll? Well, on a d6, the chance of getting the absolute lowest roll possible is 1 out of 6. Now, if we look on a 2d6, the chance of getting that extreme low roll is actually 1 out of 36, so a 3% chance. And then a chance on a 3d6 to get the lowest chance roll, 1 on 3 dice, is going to be a 1 out of 216. So the more dice you roll at a time, the lower chance you have of getting one of those extreme rolls. Additionally, we can kind of look not just the absolute extreme, but also a higher or lower average. So for example, the chance of getting a 5+ on all your dice, if you only roll 1 dice, is 1/3. Chance of doing that on a 2d6, 10, 11, or 12, getting at least a 5 on both dice, is going to be a 1 in 6 chance, or about 18%. And then getting a 5 on 3 dice, 15, 16, 17, and 18, gives you about a 10% chance. As you can see, maintaining a higher or lower average of dice gets harder and harder and less likely as you roll more dice. Now what I've done here is I've put boxes around the top and bottom 1/6 chance of rolling. So in green we have the bottom 1/6 chance, on blue we have the top 1/6 chance. You can see from our 1d6 here that they each contain just one box. Now if we go on to the 2d6, you'll see that our top and bottom 1/6 chance now contains 3 boxes on each side. And then on the 3d6, it contains 5 boxes on either side, whereas the middle tends to stay a pretty similar number, doesn't increase nearly as fast. So kind of the initial takeaway is the top and bottom 1/6 chances, or bottom 18, top 18% of any amount of dice rolls is going to become a wider and wider tail on either end along your main average as you roll more and more dice. Okay, so that's the visual part of it. We can actually look at the numbers. So on a 1d6, your average is 3.5. Your variance, not entirely important how you calculate it, but it is 2.9 for a d6. And then the standard deviation is the square root of your variance, so 1.7. And the number of standard deviations you have across the range of your dice is about 2.9 for a d6. And what you'll see as you go into the other dice is that your average and your variance increase linearly by 3.5 and 2.9 every single dice you add, respectively. The standard deviation, because it's a square root of the variance, will actually be growing slower than the variance, and that means the range over essentially the number of possibilities you have divided by the number of standard deviations is going to be increasing over time. The important part about this is that it takes more and more standard deviations to get to the extremes on either side of your probability curve the more dice you roll. Now, in this chart, what we've done is we've put the total value of your dice rolls on the x-axis, and on the y-axis is the probability of getting that certain dice roll. So for a 10d6, with an average of 3.5 for every d6, we expect that average to be right on 35, which it is. We can see that going up to a value of 50, or about 50% increase on our average, is where we start to see this kind of leveling off of our d6 probabilities. As we go up to 100 d6, we have that same average, only this time around 350, but we start to see our leveling not all the way up to about 50% increase, but instead we see that leveling off near zero at about only a 10% increase on our previous value. And this continues. The more and more dice you roll, the more and more likely you are to converge along the average. And the less likely the peripheries of your dice rolls are. The more dice you roll, the more likely you are to be rolling roughly average. As you start rolling dice, or any, flipping coins or rolling d20s, they converge on what's called the normal distribution. Now there's a lot of symbols here, but real quickly, this little sigma here is your standard deviation, so a single standard deviation. The middle here is your average. So what this is saying is that if you add one standard deviation to and subtract it from the average, that will take about 70% of the possibilities of rolls you have. So if you rolled, let's say 500 dice, one standard deviation to the left and to the right, your average will, about 70% of the time, be within inside this green little area of the normal distribution. And this works for any type of dice, any type of coin. They all converge on the standard, this normal distribution. Then 2 standard deviations away, you're at 95.5% of your dice rolls, and 3 standard deviations, you're at 99.7% of your possible dice averages. As you're rolling more and more dice, the range increases linearly, but the standard deviation increases as a function of the square root, so you'll see that it converges towards the average. If we look at for a 500 d6, this is maybe roughly the number of dice rolls you're making in a game of Warhammer 40k. The variance is going to be 1450. Square root of that is your standard deviation of 38. And our perfect average of these dice we'll call a 3.5. So a plus or minus of 3 times your standard deviation on your 500 d6 will give you an average that will land between 3.3 and 3.7. So in other words, as long as you fall within the 99.7% chance of these 500 d6, you will be within 3.3 to 3.7 average over your entire dice roll. So 1 out of 600 games, you will be outside of this average. And this is obviously incredibly extreme. It only happens once every 600 games, and that would equate to about 1/5 of your 6s being rolled in a game to become 1s. So you'd hit about 20% less, wound about 20% less, and fail about 20% more saves. This is also kind of an extreme way of thinking about it. In reality, you wouldn't just turn 6s to 1s. It would be a combination of 5s to 2s and 4s to 3s, etc. But for the example of looking at the worst case scenario, we'll turn 6s to 1s. Now, more realistically, we're going to be looking at one single standard deviation outside this curve. So being in the bottom 16% chance of probabilities. So this would happen roughly 1 every 5 games. So think of, if you go to a GT, you're probably going to get about 1 of these unlucky games. And that means your average is going to be slightly below this 3.43 to 3.50 average of unluckiness that takes place in this center, left green area. And what that's going to equate to is about 1/20th of your 6s becoming 1s. That'll make up for that average. So about 5% less hits, 5% less wounds, and you take 5% more wounds from the opponent's attacks. So that is kind of what you can expect about how unlucky you'll get at a single GT. So the takeaway from that is that people are less unlucky than they think, and having a bad dice in a game will reduce your expected damage by about 10%, roughly once per 5 games. It's about 10% because hitting 5% less and wounding 5% less, you multiply those together, and it's about 10% less damage. So you expect to have that happen once in every single GT you go to, but we all know someone who likes to complain about dice rolls for every game, for every tournament, and says that they rolled 50% more 1s than their 6s, and the chance of that actually happening is so astronomically low that it's just not really true or feasible. Humans tend to see patterns when there aren't patterns and focus on the unlucky rolls as opposed to their lucky rolls, and they're going to be a little more likely to think they're unlucky than they truly are. So what it really means to be unlucky in your game of Warhammer 40k is about a 10% reduction in damage and a 5% increase in damage taken. Anything beyond that is only going to happen, once every 100 or once every 600 games, and even then you're looking at 15 to 20% reduction in those as well. And we can look at this, how it actually plays out in the game, not just big numbers, but we can look at how the difference in attack rolls, even on a smaller scale, can really determine how effective a certain gun is at shooting a target. So this one we're going to be looking at one Meltagun, carried by a Space Marine, being shot at a Primaris equivalent Marine. So on the x-axis here, you'll see that it is the damage dealt by the Meltagun, and the y-axis is the probability of that damage occurs. So in purple is that specific value, so there is about a 45% chance that 0 damage will happen. And on the blue line here, we look at the cumulative probability. You can see that at about 2 damage right here, it's a 46% chance to do at least 2 damage. So that's how we read these graphs. So the expected damage is about 2. So on average, you will kill 1 Primaris equivalent Marine with each of these shots. You have a 46% chance of doing 2 damage, a 57% chance of doing at least 1 damage, and a 9% chance of doing all the way up to 6. Obviously that's overkill, but it's still important to look at when we talk about these dice rolls. And then if we shot 11 bolter shots versus that same Marine, you can see that the curve looks quite different. In fact, you have a 57% chance to do 2 damage, 87% chance to do 1 damage, and about a 0.5% chance to do 6 damage. Even when your expected damage is relatively lower than the Meltagun, you're still much more likely to do lower amounts of damage. The trade-off, however, is the chance at getting an extremely high amount of damage, like 6 damage here, is also vastly less likely. You have a much higher chance of doing lower damage and a much lower chance of doing higher damage. Kind of flattens the curve, so even around expected damage, the other shots with more dice are going to be more reliable in killing that Marine. Takeaway is that a large number of attacks will deal consistent damage, but variable damage weapons, such as a Meltagun, will have a higher chance of doing large amounts of damage. You could switch this out for them targeting a Rhino, compare las guns versus las cannons, and you'll always find the same result, where more dice will have a kind of lower variance in types of the damage they do, but will not have that swingy amount chance of doing a much higher damage that something like a Meltagun or a Lasgun can do. So that was Warhammer 40k Dice Math Part 2. We went over charge rolls, psychic tests, as well as variance in large groups of dice. I hope everyone learned something, and if you could, please like this video, drop a subscribe if you'd like to see more of these, and go look at Warhammer 40k Dice Math Part 1 if you haven't already. Thank you.